Well, we can develop a physiological model. That's what everybody is doing right now in disease modeling. So you look at what is normal, what are the rate constants, what are the Michaelis-Menten constants, what are fluxes, concentration, and so on. Many people have done that. We are doing that. And you do that by setting up equations, and then you identify parameter values for average healthy individuals. And now you can start personalizing these models by starting with the average model and then adjusting either singly or in combination the parameters for particular individuals. So the assumption is that everything else is sort of normal, at least in the normal ranges. And now you say, well, your cholesterol is high and your blood pressure is high and this one is low and this is so and so. And you want to put that in the model to see what the immediate effect is, what the long-term effect might be, what the effect is without intervention and with intervention. So if we compare that with what's going on right now, so here's the traditional medicine. We have epidemiology, molecular biology, biochemistry, physiology, and so on. Epidemiology gives us sort of hypothesized risk factor disease associations. You know, you get lung cancer if you smoke. Your relative risk is whatever it is, 4 times. It goes into physiological mechanisms. The physiological mechanisms usually come from animal experiments. From these mechanisms and from animal experiments, we get process parameters. That comes all from traditional biology, targeted biology. These things, physiological mechanism and process parameters and drug treatments go into clinical trials, and you get an average treatment. So you weigh so and so much, here's the dose that you should get. If we look at systems biology, there's experimental systems biology. I'm talking about microarrays, high throughput screening, proteomics, metabolic profiles, those things. It actually adds to these 2 boxes here. And if we look at computational systems biology, we can set up models of averaged people, of physiological models. We can perturb them and do simulations of diseases in the way that I just showed you. We can also look at treatments of these diseases. We can go and almost exhaustively screen for target sites, intervention sites. That's all done with numerical solution. Now, these models will allow us to do personalized simulations, as I indicated a minute ago. And so here we adjust the parameters to match a particular person. So we go into personalized health, personalized treatments, risk profiles, and so on, and then have suggested prevention. So if we look at those biomarkers, they have all normal ranges. If we put them in 2 dimensions, they seem to have little rectangles. Now we know that combinations are often not very good for you, so these boxes actually have their corners cut off, and so you get a shape. If you do that in many dimensions, you get something like a simplex. So it's like a diamond that's cut off. So if you're inside this diamond in the simplex, you are healthy. If you're outside, you are not necessarily. And we can compute, at least in principle, these simplexes from the model. So ideally, we would have a full parameter space and a full biomarker space. We would have a health and disease simplex. They are probably nested like that. And we would like something like the PSA, where we say, well, if it's higher than 4, you have a problem. If it's lower than 4, you're okay. So it looks like a plane cutting through the simplex, and you say, well, if you're on this side of the x-axis, you're okay. If you're here, you are not. Now you can see that is sort of treacherous, because depending where the other components are. So this would be healthy. This person would be healthy. A person here you don't just necessarily know. A person here would be diseased, because he is outside this health simplex. Now, as I said, ideally, we are learning how to compute these simplexes from our computational models. And it's a matter of parameters, by and large. So looking at one biomarker is clearly insufficient. One needs to do more in combinations. So if we do it in 2 dimensions, we can look at trajectories. Here's health. Here's something like pre-morbid conditions. Here is something like treatable disease and outside that is bad. So that's pre-morbidity. Here are 3 people. The first one gets a little sniffles, not too bad, comes back and is healthy again. Here's somebody who has problems, gets a pacemaker, is back. Here's a person that is not getting the right treatment, and boom. So that's a simplified version of what can happen to you. Now, we can, in principle, if we had computational models that are reliable, we could compute these trajectories along the life of a person, and at each point we could say, well, you're deviating to this side or to that side. You are not at risk of Alzheimer's, but you are at risk of metabolic disease, something like that. So in summary, modeling will not replace anything in biology or medicine, but it will complement it. So there's experimental systems biology, but there's the traditional biology, and modeling complements that. There are quite a few technical challenges. At the top of the list, at least for us, is parameter estimation. So to make the model match the actual reality. Systems modeling can play roles at several points of the drug discovery pipeline, I'm sure, and in predictive health. And if we want to go from an average metabolic or genetic or physiological model to a personalized model, I think we need to go into these models that allow us to check combinations of deviations. Physicians do that intuitively. Eventually, it becomes too complicated, and these types of models have the potential to help at least. So we have had good funding from a variety of sources, and this is my crew. It's about 1.5 years ago, and there's information if you're interested, and I'll be happy to take a couple questions.